All right, so we've been assuming with all of this biaxial analysis we've been doing that we know the stresses and strains in the X and Y directions. Let's start to figure out how you would derive them for different design situations that you might run into. So we're going to get into some more practical type analyses than what we've been doing here for a while. Okay, so the first one we'll look at is if you're designing a pressure vessel. So pressure vessels contain some sort of pressurized gas normally. So they're made to hold that kind of expanding gas. Think of pressure vessels as acting kind of like a balloon, okay? Containing pressure inside the tank. Probably the most common pressure vessel that you might run into would look like that, okay? You also see them, if you see tanker trucks with propane going down the road, you see these on trains sometimes, different types of pressure vessels. If you've ever been out to city of Salem, they have the riverfront park there. They've got the Eco Globe. It's this big sphere. That used to be a pressure vessel. That's a mill site out there. That was a containment pressure vessel for some of the chemical reactions they used to do out at the mill. They just put a mosaic on the exterior of it and made it into a kind of a cool looking globe out there, okay? So those are pressure vessels. Let's have a look at how we would analyze these. So pressure vessels, pressure tanks, whatever you want to call them. I'm on page 560. So we're doing thin-walled pressure tanks. Okay, thin-walled means the thickness of the tank is less than the radius divided by 10. That's what we're going to deal with. A thin-walled tank, you can assume a constant stress throughout the tank wall. That's what we're assuming here. Now, pressure tanks are usually made in two shapes. Cylindrical is one. They'll have half-sphere ends, hemispherical ends on them. You can imagine containing that pressure, you want the end of that thing to be bowed out, so when that pressure starts pushing on the end, it's contained effectively, okay? That's why that's done. If you got real high pressure tanks, you make them as spheres, okay? So let's look at a cylindrical tank and how we would analyze it. Now there's two types of stress that you analyze. The first is called hoop or circumferential stress. The word hoop comes from the hoop on a barrel. See, like a steel band around a barrel. That keeps the staves, the wooden slats on the barrel, from expanding out. That's the type of stress we're talking about there. That's where that term comes from. What that's trying to do is take essentially a pipe and split it in half. Okay, so the hoop stress would act in the walls like right there and right there. Okay. Now, in our analysis, we're going to ignore the ends of the tanks. They would actually add strength, but for our analysis, we ignore them, and that gets us a more conservative analysis, see? Which is often what we do when we start doing practical kind of analyses like these. We keep it on the conservative side. So what we're going to do is we're going to cut the tank right down the middle, the long way, and we're going to look at what's happening there. And what's happening is inside the tank, you've got pressure that's pushing like that, okay? And that's trying to tear the tank apart the long way. So what the material in the tank has to do is pull back, okay? So that's going to go like that. And these two forces will be in equilibrium, okay? So to keep the tank from failing, these sets of forces have to be in equilibrium. So the internal pressure is trying to pull the tank apart. The tank wall is pulling back, okay? So I have that sketched up there down below on the right. Now, what we have here then is we have, for the pressure, we're going to have a rectangular area that looks like that. Now, this will be 2 times the radius, this dimension. And then however long we're looking at will be there. So we have a rectangular area of 2r times L. That'll be an area. You multiply that by the internal pressure. Now, reacting against that, what you have there are two areas equal to L over T, with T being the wall thickness of the tank. So there's 2 times L times T, that's the area. And then you have the stress in the tank wall going back the other direction. So you got 2 times the stress times L times T is equal to 2 times the radius times L times P, the internal pressure. Well, some of the stuff cancels. The 2 and the L cancel from both sides. So you get the stress times the tank thickness is the pressure times the radius. Divide through by the tank thickness, you get a nice little formula for the hoop stress, PR over T. The pressure times the radius times the wall thickness. Okay. And that's on your formula sheet, like everything is. That's, let's see, where did that go? I think it's on the front somewhere. Yeah, pressure vessels, lower right. That's equation 61. Okay. So that gets you the stress in the tank wall if you split it down the middle, the long way. Now, the other thing that's happening, though, is if this is a cylindrical tank, there's also an axial or longitudinal stress that's trying to tear the ends off the tank. So that'll build up in this area right here. Now, what's happening there is you get a force, which is pressure times area. The area is pi r squared, and the pressure then is P. So that's P pi r squared. That's the force caused by the pressurized gas in the tank. And what's going to pull back will be the area of the tank wall, which would be T, and then the circumference is 2 pi r. Okay, so if you cut that tank and roll it out flat, you get a long, thin rectangle. The length is 2 pi r, and the wall thickness is T, so the area is 2 pi r times T. You multiply then that by the internal stress, sigma A, the axial stress. Okay, so you got P pi r squared is equal to sigma T 2 pi r. The pi's cancel, and one of the r's cancel. So you end up with PR is sigma T times 2. Solve for sigma, the stress, you get PR over 2T, which is half the hoop stress. So that's equation 62 is what that is, all right? So what we have then for a tank is, if we kind of want to go a little bit more biaxial now, we could draw a little element on the tank. And in this case, what we would have would be the axial stress doing that and the hoop stress doing that. Okay, and it looks something like that, okay? So this is kind of the process you use. You do a larger scale analysis, like what we just did. You come up with these standard design equations, then you could throw that on an element and start doing the biaxial stuff, see? That's the process. What we did earlier was we gave you the X and, or I gave you the X and Y stresses. Now we're going to figure out how you find them in the first place. Now there's no shears here. It's just like a balloon expanding out. So in the X and Y planes anywhere, there's no shear. So these are the principal stresses. So the hoop and the axial are the principal normal stresses in the tank wall, the maximum and minimum normal stresses. Okay. We doing all right with that? Okay. So if you find yourself designing pressure tanks, this is how you would do it, okay? All right. Well, on 570 then, we got a little bit of an example to run through. We got a little bit of time, so let's get started on it anyway. So now the basic things you plug into this stuff are P, R, and T, okay? Pressure, radius, and wall thickness. So have a look at the sketch and see if you can fill those things in. I get everything in newtons and meters is how I do it. I don't like getting into like kilonewtons and millimeters and stuff like that. It gets too complicated for me. So I get everything into newtons and meters and plug it in. That way, I can deal with the answer that comes out. I don't have to think too much about the units. So right at the very beginning, everything in newtons, everything in meters. So 800,000 newtons per meter squared, that's kilopascals, that's the pressure. And the radius would be half of the 1.2. Round things are usually specified by diameter. The formula calls for the radius. And then we've got the wall thickness, 10 millimeters. So that's 0.01 meters, okay? And then you just run the two fairly straightforward equations, PR over T and then PR over 2T, and you can find the two stresses, the hoop and the axial. Okay. Usually once I got the hoop, I just take half of it and that gets me the axial. So when I run the numbers there, I get 48 times 10 to the 6 newtons per meter squared for the hoop, and 24 times 10 to the 6 newtons per meter squared for the axial, just by plugging the stuff in, okay? So on these pressure tanks, you just find the pressure, the radius, and the wall thickness, and you plug them into the two equations on the formula sheet there. On the front lower right, equations 61 and 2. All right. But let's do a little bit of biaxial stuff here. Now these are principal stresses, so if you're going to design this tank, that's the normal stress you're designing it for right there. Okay, that's the biggest normal stress, so that's what I would call the design stress. Okay. That's the biggest one. But let's go a little bit biaxial on this, okay? So to do that, we need to drop our little biaxial element. So somewhere in here, we've got a little bit of a square element. Let's put the stresses on that, okay? We good? We good with all this stuff here? So we got just a minute. Let's go ahead and do that. So let's get those hoop and axial stresses on that element. Which one acts which way? Which way does the hoop act, and which way does the axial act? Okay, remember, the hoop splits the tank in half the long way, and the axial tears the ends off the tank. That's how I think about it, okay? So when I put the hoop and axial on there, they look like that, okay? So that is something that we want to remember, is that hoop isn't always X or always Y. It's splitting the tank in half the long way. The axial is not always X or Y, because it's going to tear the ends off the tank. Because you can put tanks horizontally, or you can put them vertically. I mean, you can put them whatever configuration works for your site, whatever you're putting them, okay? All right, that's that'll get us going there. We'll do a little bit more of the biaxial stuff next time. How about doing a couple of these for Monday? How about 231 and 234 for Monday? So 231, 234. We also got a couple of them for Friday, right? 221 and 221B is what I remember. So these are on pages 15A and 15B, so they're all kind of written up and good to go there. So these will be due Monday, and that will be the 9th, I think. Pretty sure. Yeah, okay. And okay, so we got our exam tomorrow, so keep that in mind. Right?